So, hi everybody. I'm so happy to be here. Thank you, Edith, for organizing this fantastic meeting. Okay, let's discuss coherent structures. As we all know, the astrophysical plasmas are generally turbulent, and turbulence develops in any flow where the energy injection scale is much larger than energy dissipation scale. That is, the ratio is related to Reynolds number. And we can ask ourselves, looking on this mass, is there any order in this disorder? And actually, as Luke already showed, first universal property of any turbulent flows is reproducible turbulent spectrum. For different conditions, we will obtain always the same spectrum. So Luke described very nicely this solar wind spectrum covering 8 decades in frequencies, and actually, indeed, we measure in situ with satellites time series, so the spectra are frequency spectra. It's satellite frame frequency that includes propagating of, if there is something propagates, it has its own frequency, and then the convection term. So we use Taylor hypothesis, assuming that the observed frequencies is just the convection of structures across the satellite to make the connection between frequency spectra and the vector spectra. And then if we add another instrument to this one, that is, so this spectrum is combined with 2 months of data to resolve large scales, -1, 51 hours of data to resolve inertial range, and just 1 hour of data to resolve these small scales. Now, if we add here another instrument, we can see that spectrum curves at electron scales, and the dissipation scale is the Larmor radius of electrons. And then the second universal property of any turbulent flow is intermittency, and the increments of magnetic field deviates from Gaussianity going towards smaller scales. What does it mean, actually? From hydrodynamics, we know that this non-Gaussianity is due to appearance of coherent structures. These are three-dimensional, quite old simulations, but the physics is still the same. And we have filaments of vorticity appearing during the development of turbulence with the length of the order of the energy injection scale and the cross-section of the order of the dissipation scale. So these structures are something to do with dissipation and turbulence. How can we define coherent structures? So Marie Farge and Kai Schneider, they propose a very easy definition that is everything that is not noise. But maybe it's not evident what does it mean, and I am more inspired by, I prefer the definition of Fiedler and Lisieux, that coherent structures are high amplitude localized in space events. As far as they are localized in space, they are delocalized in Fourier space, and they have fast coupling all over the large range of scales. They have particular topology and a long lifetime. So let's see what does it mean, how this fast coupling is related to non-Gaussianity. Let's just do a numerical experiment. We take observed data by cluster, just a piece of data, and then we do the Fourier transform. This is the spectrum, and these are phases. Okay, we cannot see anything in this map, but let's mix them up. We make them random, then we keep spectrum, and then we do the inverse Fourier transform, and we get the random fast signal. And what we see in distributions, the observed signal has these non-Gaussian tails, and the random fast signal is completely Gaussian. So these tails are really related to the coupled phases. And in the solar wind, if we model turbulent fluctuations as increments, I was inspired by somebody who showed yesterday. I don't remember who it was. It was very nice, so I just did the same. So we take differences in 2 points in our turbulent flow, and this is like our approximation of turbulent fluctuations. So then we can normalize them, and this is called partial variance of increment method. And when these coefficients are high, we catch planar structures like current sheets. So this component, this is the norm of the magnetic field, and these are 3 components, and we see that it goes from negative to positive. So these are signatures of current sheets. And we see some questions, right? so these are this is studied actually a lot in Calabria by Sergio, by Antonella, and started by Pierre and André Manginet in 1999. Now, if we approximate turbulent fluctuations as Morley-Weivlet coefficients, we can find something else, a little bit more complex topologies of structures. For example, solitons, these are 4, this is the norm of magnetic field measured by 4 satellites of clusters. So we see the shift in time. When we superpose in time and we know the separations between satellites, we can estimate scales, propagation, normal of this structure. So these are really localized structures propagating in the plasma frame with supersonic speed, actually. And so this is quite nice, but we have also Alien vortices. And Alien vortices, these are localized solutions of 2D uncompressible image D, and they can be in the form of monopoles. So this is the solution of monopole, Bessel function of order 0. It can be dipole. And what is amazing within these structures, so these are cylindrical Alien waves, we can say that, with alignments of magnetic field and velocity, but it's not like equal like in Alien waves, but we have this constant that can be different from 1. The important thing is that they are aligned. As Sergio explained to us yesterday, that is an example of this relaxation state with magnetic velocity field alignments. Okay, so when we cross monopole or dipole by a satellite, these are the signatures that we can measure. And actually, the structures has also a nice spectral Fourier spectrum. If we cross them, we can then do a Fourier transform or Weivlet analysis, and we can get this kind of spectrum with a knee around the radius of the vortex and the -4 spectrum at small scales. And this is due to discontinuity of the current on the edge of the vortex I. And if we cross dipole, it has also a knee and -6 spectrum. So actually the very steep spectra observed in the solar wind just around ion scales, it can be just a spectrum of this kind of structure that is actually present during this time interval that we checked. You will see it just later. So how we catch these structures, how we detect them in the signal. Again, let's compare this observed signal with random fast signal. And now let's apply Weiblets, Morley-Weivlet analysis. So we decompose our signal on Morley functions that are just sinusoidal, localized in space by Gaussian. And then we can normalize the scalogram by the mean spectrum, and it gives us local intermittency measure. So this is the scalogram where we have scales instead of frequencies in spectrogram, right? This is time, and this is the energy of fluctuations. We see something that is localized at large scales, energetic events, that it goes, this disappear, but when we normalize this scalogram, we see that this event actually is continuous up to very small scales. So we compare these maps now to random fast signal maps. It has completely homogeneous distribution of energy for random fast signal. So it means that these vertical lines are structures, coherent structures with coupled phases. So it will be our signatures where to look at in the signal for coherent structures. So let's go now from injection to dissipation scales and see what's going on with our data. If you consider this range -1, -5/3, we have 9 days of wind data, and we just apply Weivlet transform and we normalize it. We see this appearance of vertical lines at the scale of the break between f-1 and f-5/3. So here we do not see much signatures of coherent structures, but it starts really at the break, and it goes down to the smallest resolved scale. Now, if we take the time interval that covers inertial range and the beginning of the ion and ion scales, actually, we see again these vertical lines in the spectrogram, and they are crossing cyclotron frequency. Then this is the break scale, and these are inertial range, inertial length, and Larmor radius scale appearing here. And now we are going again at sub-ion scale. So we start here, and then we cover this range up to electron scales and sub-electron scales. We see again these vertical lines as signatures of coherent structures. So from this picture, already we can conclude that we observe intermittent structures all across the cascade, starting from the break between f-1 and 5/3, and up to even sub-electron scales. So what is the nature of these coherent structures we observe? This is an example of this inertial range ion scale transition. And just if you take two vertical lines and we go to physical space, we see the signature of a current sheet around this time, and in a signature of Alvin vortex. If we are now going to ion and sub-ion scale, this is an example of cluster, 4 satellites of cluster around the same time. So we see this localized event, and we can really estimate its shape in space, and it looks like more cylindrical than wave packet. And now if you are going in a time scale around electron scales, so it's 20 times shorter than this one. And it again shows signatures of localized vortices. So it seems that from MHD scales, from inertial range, then at ion scales and at electron scales, we have very similar signatures of these vortex-like structures. And so these are the results at 1 IU. And now the question, how these structures are connected among each other, because these results are obtained for different time intervals with different satellites. And the second question, is it the same at different distances from the sun? Is it general or not? So this is the study with Parker-Serra probe, first encounter. It's 0.17 astronomical unit. So this is the overview of the encounter, and we just take this time interval, the closest to the sun for this encounter, and we apply the same analysis. So we take we apply the Waverly transform, and we compare the observed scalogram with the random phase one. If we integrate this all over scales, we get this blue line, and this is the integration of the random phase signal local intermittency measure map. So this comparison can help us to select coherent structures. So this is the PDF of this random phase signal, and this is the PDF of the observed integrated local intermittency measure, and everything higher than this red line corresponds to coherent structures. If you take something here as threshold, we have 400 structures. And now I just show you example of 2 of them. So we are going to physical space around these vertical lines, and then we can also consider different frequency ranges. So on the left is the spectrum, corresponding spectrum of magnetic field for this time interval, and rose indicate inertial range, green ion scales, and violet sub-ion scales. So these are the original data. Around one of the vertical lines, we have a discontinuity, very clear current sheet signature. So if we just filter in the band of the inertial range, we see it more clear, this event that corresponds to current sheet. And then if we filter the data just passband in the ion scales, we have these signatures in the middle. And then we are zooming again, we have very nice fluctuation, looking like also vortices at very, very tiny scales. And this is another example that we do not see here a current sheet, but we see something else. And this is signatures of Alvin vortex at large scales. And then again, zooming in, we have these signatures of vortices. So these are the interpretation of these two examples: large-scale current sheet with vortices inside, or big, very big vortex with smaller.
Oh, sorry, but it seems that there is also a parallel component to the mean field, correct?
At very small scales.
Yes.
At very small scales, yes.
So
yes.
like they have a flux rod-like structures, right?
It becomes compressible, right? Yeah. Actually, I'm at the point now to try to understand these guys. And the polarization, if this one is more like Alvenic, uncompressible in the plane perpendicular to the field.
No, I was thinking about the helicity.
The helicity.
Probably there is an out-of-plane component apparently.
Yeah, we need to discuss it in more details, yeah, in the blackboard, yeah. Thank you, Serge. So now these were just two examples, but we have thousands of them, and it's quite difficult to go by eyes through all of them, but we can apply minimum variance analysis around each one in an automatic manner. So what does mean minimum variance analysis? This is the magnetic field covariance matrix, and so it helps us to understand in which direction we have the maximum of fluctuations of magnetic field, minimum of fluctuations, and then there is an intermediate direction that, so we order them in like the urgent values are organized that one corresponds to the maximum variance direction. And if we now represent our data in the plane of this anisotropy, so the ratios of these urgent values, we can see them raw data give this result: MHD scales, ion scales, and sub-ion scales. If we had completely isotropic fluctuations, the three urgent values were of the same order, and the ratios were 1, right? So 1 means this corner. So if it was random fluctuations, it was here. We see that the data are mostly here. What does it mean? What does it mean, this stuff, actually? So we take different possible models of coherent structures, like Alvin vortices, current sheet, magnetic hole, and then we cross it on different trajectories. What is shown here is like blue trajectory give these signatures of magnetic field. This is the signature of a current sheet, crossing by this trajectory, I think, and this is the signature of a magnetic hole. So now if we change trajectory, we make thousands of trajectories, we can try to estimate these urgent values, and we see how it will go for Alvin vortices. This is like current sheets, and this is magnetic hole. So the data looks more like magnetic holes. We do not see them in the data, but mostly it seems that we have vortices or a little bit of current sheets, and we did more sophisticated study I have no time to go through, but we find that it's 90% of data corresponds to Alvin vortices and only 10% to current sheets. So now just I'm coming to the end of my presentation, just a small discussion of what is a widely accepted picture of the solenoid turbulence. So usually we think about that in the inertial range, it's just Alvin wave propagating from the sun, critically balanced, and then arriving to ion scales, Alvin waves became kinetic Alvin waves, and then at sub-ion scales we have the critical balance cascade of kinetic Alvin waves, and then dissipation of these waves by Landau damping. Okay, very good. And this is actually consistent with some mean properties of turbulent flow, like turbulent spectra. It was shown that perpendicular wave vectors corresponds to -5/3, parallel wave vector spectra follow -2, so it's consistent with critical balance. Then dispersion relation of very perpendicular kinetic Alvin waves is consistent with the data, but actually these data are also consistent with convected coherent structures that are not compared here, because the idea of the paper here was about waves, but coherent structures are just here. And then compressibility. Compressibility is the parallel spectrum of parallel fluctuations over the total energy, and it increases with frequency, and it's also consistent actually with properties of kinetic Alvin waves. But where is intermittency in all this story? Here we see only waves, right? But we just saw clearly that we have we have coherent structures that starts to exist at the break between injection and the beginning of the cascade. So as far as cascade is there, coherent structures are present, and they are going up to sub-electron scales. That was the resultant 1 astronomical unit. Then closer to the sun, we show that there is this embedding of structures. Kinetic scales vortices are sitting inside image scales vortices, like Russian dolls, and we have the dominance of these signatures of vortices at all scales. So it seems that magnetic vortex is an important building block of turbulence, and coherent structures in general are important part of turbulence. So what about the concept of the cascade, actually? Here we have like cascade idea, right? It's from large scales, we are going to smaller scales, and then we dissipate. In coherent structures, we have all scales coupled with the same phases at the same time. So I have this philosophical question. Let's discuss maybe during coffee breaks. And then the role for the particle transport of particles. Sergio showed to us very beautiful test particle simulations, how they can be trapped or accelerated, and of course connection to other astrophysical systems. So for example, beautiful results of Pierre and Thibault in 2022, studying numerically the compressible image D numerical simulations to explain interstellar medium turbulence, and they have like different types of possible coherent structures, like sheets, ribbons, or tubes. And I like these ones, tubes. And these nice observations of galactic interstellar medium filaments by Loeffler and Planck, showing us this beautiful filament, or the one that Marc-Antoine showed us yesterday. I just make a photo during your talk, I'm sorry. But I think it's something that we can think about, how it's related to the Alvin vortices. Thank you so much.
Questions? Probably yes, of course.
Thanks. Very interesting talk. First, I wanted to say in subalfanic guide field experiments in turbulence, we find these vortices everywhere. They are, at the outer scale of the turbulence, rotating around and around, and they live forever. They literally live forever. I just wanted to know two things about your vortices. What sets the outer scale in, what sets the 1 AU? Are these force-balanced kind of systems? And also, what is the vortex profile? So as what's the VR?
BR. Okay, outer scale. Of course, crossing a vortex along the axis will not give us any signal. It will be constant. So, the only way to catch it, the only way to catch it is to cross it perpendicularly, and then the radius of the vortex, it seems to be like 10, 20, 30 inertial lengths of ions. That it was like the first detection. The first detection, we find them behind the bow shock of the Earth in the magnetospheres, and it was like this kind of scales. Then we find them as well behind the Cronian, the Saturn bow shock, also like 10 inertial lengths of ions. And this actually sets this knee on the spectrum, and it was like always on this ion break. They were like, the smaller scale actually of these large scale structures was iron scales. But
Yep.
then we observe them as well at much smaller scale. So
Yeah.
I'm still thinking how to connect them.
Are they pressure balanced? Like what keeps them at a particular scale? Do you understand that yet?
Yeah, what gives them particular scale? Transition from ImageD to other physics. I
Okay.
think these give them the outer scale
Yes.
or the smaller scale at ImageD scales.
Yes.
But then the properties change. So if we are going to, I haven't showed it here, but with cluster I tried to understand it up to electron scales. The polarization is in the plane perpendicular to the field, and then going to electron scales, it becomes field in the field and one perpendicular direction plane. So it's really like I'm not. It's not still clear in my mind.
Okay. Very cool. And what is the vortex profile? Is it a solid body vortex or is it a shear?
But
Does it have a shear layout?
you just saw it. The profile is this one, for example. This is the vortex profile. So this is the thing that you can fit with the vortex model. Yeah.
Bill?
Very nice talk, Olga. Hello.
Thank you. Yeah.
So these are a special kind of flux tube with alphanic alignments and so forth.
Exactly.
So as such, they would be potentially derived from some Euler-Lagrange principle or some relaxation. They're relaxed flux tubes. So when you say that they're part of the cascade, fine. But is the cascade consist of, in your view, consists of the interaction between these different vortices, or is it something happening within the vortex, or is it happening in the spaces between different vortices that are not vortices? Seems to me there are several possibilities. Or maybe all of the above, I don't know.
I think it's all of this, and I think if we take off vortices from the signal, we do not see any more -5/3. I think so.
But in terms of the dynamics, I mean, is it...
In terms of dynamics, I think it's inside and around, and
And the spectrum cannot tell you the dynamics, right?
Yeah, it's a bit of similar questions. You had these slides where you commented or you express the visions of various scientists on what are the intermittent structures.
Mm-hmm.
And so you mentioned the vision of Farge et al. As being not noise and others as being like coherent structures. In the algorithms, when they decompose the algorithm that you use with the wavelets, you make the separations between a background and the structures. And it turns out that, this is a bit of a similar questions. Do we sufficiently understand the nature of this background? Is it sufficient? Is it exactly noise? Does it play a role in the cascade?
Yeah, indeed, when I mix phases, I do it drastically in the way that maybe in the background it is just small amplitude. So mixing phases makes it random. And I focus on these structures. And you are asking me about what's going on around the structures, right? I think around the structures there are smaller amplitude, maybe other structures. But how random they are, it's not clear. Yeah, it's something to think about. Yeah.
Okay.
I think everything is connected. There is this information everywhere.
Somehow they're at the top of the iceberg, but what information is encoded into the regions which are not directly identified by this kind of algorithm? Because there is always some degree of arbitrariness in what do you define, where you cut.
Yeah.
Depending of the threshold that you set, you find different answer. We play around with this. We apply this algorithm in the context of the ISM. We identify the down structures, but there is all the diffuse gas that I think out of which the dense structures will form.
Yes.
And certainly it contains a lot of information.
Yeah, exactly. Thank you.
Okay, let's thank again our